Hello and welcome back to Historical Geology. Today I want to finish off chapter 12 and looking at some of the Paleozoic communities in terms of the invertebrates. Trilobites. There are new experiments going on and we're going to see that trilobites are important. We'll see brachiopods and archaeocyathids are the important organisms. And we talked about archaeocyathids. Remember, the key thing about these guys is they were the reef builders for the Cambrian, and they went extinct at the end of the Cambrian, so they become really good index fossils. We also had some strange short-lived experiments like this helicoplacoid, which is related to echinoderms. Also, during this time, we had the Burgess Shale. Remember, we talked about how this was a well-preserved fauna that shows us the complexity of the ecosystems during this time and how life was experimenting, trying to fill out these new ecological niches. Other things about the Burgess Shale, remember, it's mostly Cambrian and it was remarkably preserved because the criteria for making a good fossil is rapid burial, low oxygen, and hard body parts. Most of these fossils did not have hard body parts. So what happened here, the idea for Mount Field, or the geology there at the time in the Cambrian, it was a reef system at the edge of a deep slope that would go off to the deep part of the ocean. And there were occasionally landslides. So the community would suffer a catastrophic landslide to deeper waters. And that landslide, well, one, you'd get the rapid burial, and two, deeper waters have lower oxygen content. So that's why these fossils were well preserved. Here is a fossil of Hallucigenia, which is related somewhat to maybe a velvet worm. And then these are actually the jaws of an Anoxia, the predator of this Cambrian time. The next period is the Ordovician, and the key thing about the Ordovician is that we have this great biodiversity. In fact, it's called the GOBE, the Great Ordovician Biodiversity Event. And in terms of the fossils, it's just as impressive as a Cambrian explosion. Maybe there was another boost in oxygen levels, and we really start seeing the first true fish develop, the Agnatha or jawless fish called ostrigoderms. These were armored fish. We see this great evolutionary radiation of life also occurring in the Ordovician, where these ecological niches are being filled by many organisms. Two groups show dramatic evolution during this Ordovician time, the graptolites and the nautiloid cephalopods. We talked about graptolites already. Remember, they're colonial, going to be in these little carbon films. They're planktonic. When they die, they sink to the sea floor. They're abundant in Ordovician, Silurian, and they went extinct by the Mississippian, so they become really good index fossils. The other group are the nautiloids. So nautiloids includes the chamber nautilus and the extinct ammonoids, as well as some of these baculites, which have straight shells, and large ammonoids or nautiloids that lived during this Ordovician time. In fact, some of the nautiloids of the Ordovician got up to 6 meters long, so enormous. They were the predators of this Ordovician sea. Marine cephalopods, remember, that would be the class. They belong to the phylum Mollusca, but the class is Cephalopoda, which is head, foot. We have the baculites, the ammonoids, and remember, we talked about this already. The sutures get more complex over time, and that's how we can figure out the ages of these organisms. So here's some reconstruction of a baculite and a nautiloid right here. Also, this marine communities in the Ordovician they really diversified because we had the transgression of the Tippecanoe Sea. This transgression created all these new ecological niches for these organisms. And we really start seeing the articulated brachiopods, the ones that have the hook. We also see bryozoans, corals, and these organic shelled phytoplankton called acritarchs. More complex acritarchs develop. Also, bryozoans, stromatoporoids, tabulate corals, rugose corals, they become the major reef builders. Here's some images of these organic walled acritarchs. So they were primarily the food source for suspension feeders. So acritarchs become a very good Ordovician index fossil based on their complexity. For brachiopods, we see that 50 to 90% of Cambrian life were trilobites. The second most abundant group were these articulated brachiopods. And so the key thing is they have this hook, and note that their shells on either side are different. Now, for the bryozoans, remember, they also have that lophophore, and they first appeared in the Ordovician, and they were abundant in the Paleozoic. So here's that example of the lophophore they used to capture plankton. They were suspension feeders. And here's the Phenostella that I've mentioned before. We talked about conodonts already. Conodonts are also important fossils for the Ordovician and really through the Mesozoic. We talked about the stromatoporoids, which are phylum Porifera. Remember, these guys were the Ordovician reef builders. So remember the Cambrian, we had the archaeocyathids. For the Ordovician, we're starting to see these stromatoporoids related to sponges, but they also left these calcium carbonate secreted fossils here. Other reef builders included the corals. So we have the horn corals, which is the rugose or rugosa corals, and then we have the tabulate corals. In this case, this one's called a halicite right here. So the rugosa corals are the horn corals. They went extinct. And the tabulate corals have these tabulae and chambers, and they also went extinct by the end of the Permian as well. And they were massive reef builders during this Ordovician time. So this end Ordovician mass extinction, we saw over 100 marine invertebrate families go extinct. About half the brachiopods and bryozoans in North America go extinct. And what was happening here is we see Gondwana moving over the South Pole, which means we're going to see the regression of the sea, and that's that Tippecanoe regression. But by Silurian time and Devonian, we see a bounce back. So after the end Ordovician extinctions, brachiopods, bryozoans, gastropods, the mollusk bivalves, corals, crinoids, graptolites, they all rebound to start the Silurian period. And again, this is marked by another episode of reef building, but again, we're seeing the stromatoporoids and the tabulate and rugose as making the dominant reef builders. Also in the Silurian time, we're seeing brackish waters in some of these continental or epicontinental seas, the Pyrex seas, and we start seeing these giant arthropods called euryptids. And euryptids were really the predators of the Silurian Sea. Large scorpion-like, they had large pincers, expanded to brackish and fresh waters, and these were really the predators of our ancestors, the fish. And so the end Devonian mass extinction, we see a massive collapse of marine reef communities. We don't see much effect on land for the land species, but we do see quite a bit in the tropics in terms of marine organisms are affected because they really can't move to any warmer waters. Although high latitude organisms, they can move closer to the equator, so they weren't as affected as much. So there must have been some sort of global cooling. We know that this time we're seeing the closing of the Iapetus Ocean. That closing of that Iapetus Ocean, we lost lots of habitat, all those continental shelves. Now for the Carboniferous and Permian periods, we see a bounce back. Again, there's adaptation, rediversification, brachiopods and ammonoids quickly recover. Massive reefs are replaced by small patch reefs. So that's another thing that's going on here. We lose that big reef system, but we go back to this patch reef system. Crinoids, blastoids, which are these echinoderms, lacy bryozoans, brachiopods, calcareous algae dominate these waters. And we see a species of foraminifera called fusulinids, which are single-celled organisms, and they were really abundant in the Permian period. So for the stock crinoids, we've talked about these already, were extinct at the end of the Paleozoic, but they were very common to the Mississippian and somewhat to the Permian period. Again, they were suspension feeders. Then for the fusulinids, there's a new form of foraminifera, so they accrete calcium carbonate from seawater, so they leave a hard body part. They lived in shallow seas, so they were benthic. They're single-celled, so they're amoeba-like, but they make this calcareous shell here. They're half a centimeter to up to 10 centimeters in size, so they're quite large, very characteristic of the Permian, and they're a good index fossil. So here's some fossil fusulinids here as well. And then by the end of the Permian, we see the greatest mass extinction that Earth has experienced, and it's also known as the Great Dying. 96% of marine invertebrate species go extinct, and these include the rugose corals, the tabulate corals, several bryozoan classes, several brachiopods. All of the trilobites go extinct, as well as the blastoids. 70% of land species go extinct, many amphibians and insects, so it's a major mass extinction. So this extinction extended over 28 million year period, and it was broken down into two extinctions, one at the end of the Guadalupian and then the terminal mass extinction, and I'll show you a figure of that in a moment. Some people say, well, maybe the extinction was caused due to Pangea forming and reduction of shelf environment, shallow water environment. But Pangea had already formed before this end of the Permian, so it really probably wasn't due to that. And then another suggestion is that maybe glaciation caused this mass extinction. But glaciation had already ended by the Carboniferous, and so the sea levels were actually rising during this time. What's more likely is there was this episode of deep anoxia. In other words, the ocean somehow wasn't circulating enough to bring oxygen-rich waters to deeper levels. And so that's this concept of a thermohaline current, where you're bringing cold, salty waters to the deep ocean. And those cold, salty waters usually have higher concentrations of oxygen. So there's this concept here called thermohaline circulation, and it's really the ocean's great conveyor belt, where we're mixing waters vertically. The key thing, we're taking oxygen-rich waters and bringing them down to the deeper ocean. So we're mixing that. And we find that this thermohaline circulation is 90% of ocean mixing. And it brings those oxygenated waters to the deeper zone in the ocean. So remember, thermo refers to this cold water. So we're seeing the cold waters primarily when sea ice forms. So sea ice forming at these high latitudes, salt lowers the freezing point of water. So when sea ice is forming at -2 to -3 degrees centigrade, 27 to 28 degrees Fahrenheit. So that's below freezing. So the water is super cold, colder than freezing water, because remember, salt lowers that freezing point of water. So it's very dense and heavy, and that's going to allow it to sink. Whereas haline refers to the salty part. Sea ice, when it forms, has no salt. It's really fresh ice. So where does all that salt go? Well, it stays in the water. And so what happens is that the water becomes hypersaline and super cold, very dense as well. So what happens is that we see these vertical currents where water just drops to very, almost like a rock, very heavy waters. And it's bringing all that oxygen that's up here, that O2, which is free oxygen, bringing that oxygen down to these deeper ocean levels. And that's what we're seeing today, and especially from the Antarctic, where we're seeing very cold waters due to the glaciers that are down over here. So again, we're bringing that oxygen from near surface waters down to the deeper ocean, and that's mixing the ocean. What's happening, or at least what believed to have happened in the end of the Permian, is that this stopped, which means that there was no oxygen being brought down to the deeper levels, and we get a period of anoxia, or no oxygen in the deep ocean. And there's really good evidence for that. Now, what could be contributing to this? So, raising atmospheric temperatures, toxic amount of greenhouse gases being added to the atmosphere. And so these Siberian traps, this is a large igneous province, mostly flood basalts. They erupted for about 2 million years, and they span that Permian Triassic boundary. That timing is perfect. And these basalts cover a 4 million cubic kilometer area, which essentially covers almost an area of the United States, the 48 states here. We find that oxygen isotopes tell us that the peak extinction underwent lethally hot global warming, where equatorial ocean waters got to 40 degrees centigrade, over 100 degrees Fahrenheit. Today, equatorial waters are 27 degrees, or about 80 degrees Fahrenheit. So very warm. And then people at MIT in the last 10 years have really tried to figure out the timing for these Siberian traps, and they find that they began about 300,000 years before the mass extinction, and they ended about 500,000 years after. So they're right, the timing is perfect for those volcanic eruptions. And this chart kind of shows what was happening. So during this Guadalupian time, which is toward the end of the Permian, we see a lot of red hematite chert. So red hematite means we're oxidizing. There's oxygen in the ocean. So remember, chert is a rock that forms in the deep sea, mostly from radiolarian ooze. And the fact that it's red means there's oxygen available for rusting that hematite. Remember, hematite's an iron oxide. But then at the end of the Guadalupian, we see gray chert. So no more red, which means no oxygen. We don't have oxygen to oxidize that iron, and so we see gray anoxic chert. And then there's a terminal Permian mass extinction here, but we don't start seeing red hematite chert not till the Triassic years. So again, we're seeing this evidence of low oxygen in the deep sea, right? Deep sea anoxia lasted for about 20 million years.